All right. Hello, everyone. Today, my name is Vedatman Duhoon, and I will be teaching projections and vector components, a subtopic in 11.3. All right. The first thing we need to ask ourselves is, what does it actually mean to project a vector? Well, let's take an example. Let's say you have vector A, and you have another vector B. What does it mean to project A onto B? Well, in everyday language, project usually means to cast. And in mathematics, it's pretty similar. The best and most intuitive way to understand this is think, what would the shadow of A look like on B? Or what part of vector A would be on or lie in the direction of vector B? An intuitive example to think of it would be, imagine if we had a source of light, like the sun, at the top of vector A. What would the shadow look like? That's right. The shadow would be this portion right here. And this portion is known as the vector component of A along B. Essentially put, it is the part of vector A that lies in the direction of vector B. All right. With the intuitive understanding out of the way, let's try to figure out if we can form a mathematical formula to deduce a relationship between these two vectors. Now, we have vector B over here, and we have vector A. What do we know about these vectors? Well, we know that the projection of A onto B is just this component over here, this blue component over here. We can call this the magnitude of the projection. Meanwhile, we know that this length over here is the magnitude of the vector A. And this is the angle theta between the two vectors. How exactly are we going to create a relationship between this? Yes, we can use the cosine formula. Recall, cosine is just adjacent over hypotenuse, which in this case means the adjacent vector magnitude over the hypotenuse, which is A. With a little bit of rearranging, we have the magnitude of the projection is equal to the magnitude of A cosine theta. Recall from earlier examples that cosine theta, or earlier lessons, I should say, and cosine theta is just equal to A dot product B over the magnitude of A multiply the magnitude of B. And if we plug that back in, we notice that the magnitude of A's actually cancel out. Indeed, the magnitude of A's are going to cancel out, leaving just the magnitude of B, making the final formula of the magnitude of the projection A dot product B over magnitude B. Now, are we done? Not at all. This over here is just the scalar projection, because all we're dealing with here is the magnitude, or the length of the shadow. But vectors are not scalars. Vectors are not scalars. They have direction. So how can we incorporate direction into this formula? Well, if we're looking to keep the direction of the B vector, all we need to do is multiply by the B unit vector. Now, why is that? That's because the B unit vector has and preserves the direction of B, but is a magnitude of 1. Meaning if we multiply it with our scalar projection, it's not going to impact the magnitude of our scalar projection, but introduce the direction we so desperately need to describe vector projections. As a result, the vector projection is going to equal the scalar projection multiplied by the unit vector. Multiplied by the unit vector. All right, so if we just write that out, we get A dot product V over magnitude B multiplied by B over magnitude B, giving us A dot product B over B squared times B. Perfect. Now, keep in mind that what we've done here is, again, the vector component of A along U. The key word here is along. There is another portion. There is another portion right here. This portion is, as you can see, orthogonal to B, and is also a component of the vector A. This is the vector component of A, orthogonal to B. And that makes a lot of sense. Again, remember, it's because this over here is orthogonal to B. All right, or we can also call this W2. Some of you may be wondering why this is just the length. I just initially did it as the length because we hadn't gone over the vector projection yet. If you make this an arrow, it would be 1. If you just keep it as just the length, it would be the magnitude. All right. Now, with our formulas in hand, we can start looking at problems. The first one is this. We have U, we have V, we have the first projection, aka the projection along V. We need to find VW2, or again, the orthogonal component, or the vector component of U orthogonal to V. Now, how are we going to go about this? Well, it's quite straightforward. Let's revisit how vector addition works. Let's say we have vector A, and we want to add it to another vector B. How are we going to add these two vectors? Well, all we need to do is rearrange them from tip to tail, and then draw a new vector. We need to draw a new vector from the original point in the first one to the end over here. And this would be C. And we know that C is equal to A plus B. A plus B. Similarly, in this example, we have the component U. And it is made up of W2 over here, W2, and W1 over here. If you compare the diagrams, they're identical, and this shows you that U is just equal to the first projection along plus the other projection orthogonal. That is because, again, when you add up the components, you get the original vector based on the properties of adding vectors. From here, the rest of the process is simple. Remember, all you have to do is isolate for W2. You get W1 minus over here. And from here, the maths are pretty straightforward. All you would need to do is just input the specific values for each of the things. So 7 over 4 here, 4 and 6 here. Subtract each component individually, and you get the final answer, 3 and -2. All right. With that established, there's another thing I'd like to point out. Keep in mind how this vector V over here is much smaller than U, but that doesn't really impact the final projection. It doesn't matter if V was this long or if V was this long. And the reason is because all we really care about with V is the direction. Because the direction is what's going to tell us how much of U lies along V. Similarly, that means if the angle is obtuse, let's say, it doesn't really impact how the projection goes. All you would do is you'd continue projecting down. This would be the component along, and this would be the component orthogonal. But this idea that the length of V matters less than the direction is going to become very important in our next example. A 600-pound boat sits on a ramp inclined at 30 degrees. What is the force required to keep the boat from rolling down the ramp? All right, for this example, let's draw a diagram. We have an inclined ramp at a 30-degree angle. We have a very crude drawing of a boat, and we need to input the 600-pound boat. Now, this 600-pound is the weight of the boat. And weight, what is weight? Weight is the force exerted downward by the Earth. As a result, this vector right here points straight down. Let's call it F, and it would be negative 600j, as it is in the vertical direction and it is going downwards. Now, what vector would describe this ramp? Let's call it vector v. This describes the ramp. What we need to do now is figure out the force required to keep the boat from rolling down the ramp, i.e., we need to figure out what part of the force of F lies along V. We need to figure out what part of F lies on V. That sounds a lot like projecting vector F onto vector V. And if we do that, we get W1. And W1 is going to be the force that is exerted along the ramp to the boat. And the magnitude of the force is going to be what we need to keep it from rolling down the ramp. All right, we have intuitively discussed why and what we need to do. Let's write out the formulas. We know W1 is simply going to be the force times the vector V over the magnitude of V squared times V. Now, what do we make V? Because it wasn't given to us in the problem. I'm going to make it a unit vector. But why? Why would I make it a unit vector? Well, remember, 1, the direction matters more than the length. This is key. It means that the length could literally just be 1, and that would simplify our calculations massively, because the denominator just becomes 1. As a result, when we take a unit vector, our mathematics becomes much easier, while at the same time preserving the direction and the final answer. So what exactly would this look like? Well, it would look a lot like V is equal to cosine 30 degrees I plus sine 30 degrees j. And the reason is because if we take the magnitude of this, it'd just be cosine squared plus sine squared 30 degrees, which is just equal to 1. All right, with that in place, the denominator becomes 1. We take this dot product over here. Remember, because there is no, let me write this here, there is no I component, it is just 0I, which means that when you take the dot product and multiply 0 by cosine 30 degrees over here, you just get 0, meaning the only thing in this dot product is going to be negative 600 times sine 30, just 1/2. And then, of course, you take the vector again, which is just negative 300 times, again, the unit vector, which in this case would be cosine 30 degrees I plus sine 30 degrees I, or 30 degrees j, my bad. And now all we need to do, that we have W1, is figure out the magnitude. Well, this over here is just a scalar, whereas this is a unit vector, meaning that the magnitude is just going to be this unit vector multiplied by the scalar, which means the magnitude equals 300. Now you might be wondering how I got this number. Well, all we can do is distribute fact check this, all we need to do is distribute the 300 back into the vector. And if we do that, and then take the magnitude, we'd be able to get 300 squared cosine squared 30 plus 300 squared sine squared 30. This will just equal 300 squared, or 300, which means we can comfortably say the magnitude is 300, and the final answer would be 300 pounds. This is how a real-life application of these projections will work. And for a more book example, more traditional example over here, all we need to do is solve this problem manually. Remember, all we need to do here is employ the formula. If we are projecting u onto v, we're projecting u onto v. All we're going to need to do is take their dot products over, v dot products over v squared multiplied by v, which in this instance is going to be 13 over 26 times 5, 1, which equals 5 over 2, 1 over 2. And the way I arrived 26 was just, again, taking 5 squared plus 1 squared. And the way I got 13 was, again, 2 times 5 plus 3 times 1. All right. And in order to find the orthogonal component, remember, u is equal to w1 plus w2, as previously discussed. That means that w2, or the orthogonal component, is just u minus w1. You input the correct values, which you input the values that we just determined in part A, and you get the right answer, which is, again, negative 1/2, 5 over 2. End of the day, that is all you need to know about projections and vector components by Vedatman and Duhoon.